Okay, we're going to try this again because we had major microphone issues in class today, and it took a little sleuthing to figure out what the problem was, but we've got it fixed. So, controlling chemical reactions. So, how do reactions get started? This is actually a question someone asked on their homework. Typically, reactivation energy right here that we're talking about, all reactions require activation energy to get started. Most of the time, it comes in the form of thermal energy, but not all the time. So the minimum amount of energy needed to start a chemical reaction is your activation energy. And all chemical reactions require a certain amount of activation energy to get started. So when we start looking at those graphs, for example, that were part of your homework, you'll see that it's a little hill shape, and that's because you have to reach a certain amount of energy before you can start the reaction. So what affects the rate of chemical reaction? Well, there's a couple of different things. There are factors such as surface area, temperature, concentration, the presence of catalysts, and inhibitors. So let's look into surface area. So the reason I chose this picture, and we talked about this in class, is that there are some leaves here, and they're a great example of how a chemical reaction can proceed at a faster rate when you have greater surface area. Trees really take advantage of this. So the chemical reaction that goes on inside of leaves that we're discussing at this point would be photosynthesis. And these are leaves of a deciduous tree. So that's a tree that sheds its leaves in the fall. So having these nice big flat leaves is really helpful because it can allow for faster reaction rates and within the time frame that the leaves are actually on the tree, which is limited, you can get more reaction done, which means you can produce and store more energy. If you think about a lot of evergreen trees, like pine trees, for example, they have a decreased surface area in their needles. Their leaves are needles, and they keep their leaves all year round. So they have 365 days in which to get the same amount of energy produced and stored as trees with leaves have in the spring and summer months. Another thing that can affect the rate of reaction is temperature. Increase in temperature typically increases the speed of reaction, and this is because when you increase temperature, you increase the kinetic energy of the molecules or particles, whatever they may be, atoms within the substance. And when those start moving around faster and faster, they're more likely to bang into each other, and that will increase the speed of your reaction. Likewise, and conversely, I guess, decreased temperature is going to decrease the speed of reaction because everything is moving slower. Another thing that affects the rate of reaction is concentration. So concentration is how much of something or the amount of a substance in a given volume. And increased concentration is going to increase the speed of reaction. And if you think about there being a certain amount of particles present within a solution, for example, so like look at one of these flasks and think, okay, well, there's a certain amount of particles of my reactants available in that solution right there. So if I have more of them, they are more likely to come in contact with each other versus if I have less of them or a decreased concentration, we are going to end up decreasing the speed of our reaction because it's less likely that they're going to bump into each other. When we decrease concentration on purpose, it's typically called diluting, and we can do that with water. In the lab today, we used some diluted hydrochloric acid, and that had been diluted with water. Catalysts and inhibitors. So catalysts are going to increase the rate of your reaction. Inhibitors are going to decrease the rate of your reaction. Sometimes you want your reaction sped up, and sometimes you want it slowed down. And then also you have biological catalysts called enzymes, and they function to increase the rate of reaction inside your body for all the various chemical reactions that your body completes on a regular basis. So if we look at our homework real quick, I will show you, whoops, sorry. I'm going to make sure that you guys got the answers for this. And, sorry, I have too many things up. Okay, here we go. So for your homework, you guys had two graphs. One was an endothermic reaction, one was an exothermic reaction. So here's how these function. When asked the question, use what you know about endothermic and exothermic reactions to explain the differences in the graphs above. So what you're going to notice is that both of these reactions are going to require activation energy to get started. Your activation energy is added like right about here, and it starts to increase until it gets to this tipping point. Same thing here. And what you will notice is that in the exothermic reaction, your reactants have higher energy than your products. And in your endothermic reaction, your reactants have lower energy than your products. So the reason why your activation energy is pictured as a hill is because, as we were saying, you need to build up to the point where your reaction can take place. And then explain how adding heat to reactions shown in the diagrams would change the rate of chemical reaction, and name two other ways you could change the rate. Well, typically if you're going to add heat, well, usually your thermal energy is what's going to start your activation energy, though, like I said, not always. But if you add heat, it's going to speed up your reaction. And some other things you could do is you could add a catalyst to speed it up or an inhibitor to slow it down. You could also increase the surface area. So here, I'll leave this up for just a second so you can check these, but these are book answers basically. Okay, I think that covers all of that for you guys. Sorry about the microphone issues today. That was a nightmare, but we got it. Thanks. Two, three. No, blow gently.
Yummy.
Jack, move your hand so we can see what you've got. So there you go.
Jack, it's
There, they're going. Keep going. You might have to take a couple breaths and do it a couple times.
Guess what? I told you. What kind of easy making?
Careful. You're fine.
Jack, it's okay for you to drink.
No, it's not.
Drink it. You gotta hydrate.
So check out what's going on with Alex, though. What's he? Look at that. If you keep blowing, it should go all the way
I
yellow.
got it all on my paper.
Oh my gosh.
I'm too focused on Alex's
There you go. So who had the water with dye?
I think it was Alex.
Smart Alec. Yeah, very clearly Alex has.
Alex over there.
Let's see.
I'm still trying it. Keep
Quite
doing it.
yellow. Very good. See yet? It's already. See how it's already dark now? It's no longer copper. Keep watching. It's gonna grow. It'll be really cool. It'll get really fat, actually.
It'll get thick.
It's one of those little growth plates you can water while it grows.
Whoop! He shot out! That never happened.
Where'd he go?
It's like a cannonball. Get in there.
Oh.
Get in there.
Get in there. How did you
That is crazy. They don't ever do that. Oh, he's sliding. Uh-oh. He's sliding to his death.
Thing?
Come on.
Hey, we don't encourage suicide.
Yes, we do.
Drew.
Wait.
Drew.
He's sliding to his death slowly. That's funny. I've never seen one do that. They usually just.
Oh, there we go.
Whoa!
Whoa.
Whoa, what the heck?
But
Oh.
he was definitely screaming. Okay, wait.
Half of it shot out.
Let's try the lemon guy.
Wait, okay.
The red one wanted to live too much. You gotta put a different one in.
No, it's still good. It's still got
Love
that.
the exit.
That was weird.
I should have. He already died.
Hey, Michael, you want to eat the charred ones? Go for it.
Actually, can I? That's a good idea, Michael.
If you bet me money, I will 100% eat the cherry.
How much money?
I am.
Get in there. Go,
I will give you
go, go, go.
Drew, yell and go is not going to do it.
That's crazy.
Or
Mom, try opening one of the tongs. Like, try opening the tongs and then sticking one end of it down.
No, I'm not doing that. Come on, scream. Look at him, he won't scream.
You might even know that Brazil never really tested.
There he goes. It's slow. You're acting like a robot.
This is not.
Just put your mask on.
There you go, Cole. That low.
Victory time.
Hey, if there's ever a fire, you get on the floor, okay? So heat rises.
You're also like getting every bit of the smoke ever.
That's crazy.
I know how that works.
That smells good.
Well, now it's all kicked in there and it won't
Your
come
video
out.
got
So
pretty bad, Mom.
let's go. Oop, he jumped again. Is he gonna slide back down?
Yeah.
He's coming.
He's
sliding.
He slides down. He's down. It's a trampoline. Yeah. Flying.
There you go.
Why are you standing in front of it?
Yay!
Good.
I think I was supposed to break the ring.
Yeah, I couldn't get him on right. Don't worry about it.
So sodium carbonate hydrochloric acid. We put carbonate. Okay, so what happened? Your reaction?
A little bit more. Now stir it. I close it up. And am I done stirring yet?
I think you're right. Four.
It's like water.
Wait, but we could put this in and see if it burns it. It's
Don't go, especially not on your. No, I accidentally put it down.
Ready?
Great job.
Okay, so what do you think is gonna happen?
Okay, I'm just gonna stand here with this.
You think it'll fit?
I think it'll
Okay,
fit.
it's gotta come over and say, put your weight in.
Oh, fun.
It's blue!
Okay.
Don't put your face to it. Never do that.
Bad idea.
Oh, it's getting hard.
See if you can get it close to the fire.
Oh, what's that?
Get 2
It
milliliters
changed color.
of copper sulfate. Copper sulfate. How am I supposed to get it in here?
That's interesting.
How on earth are you supposed to write that down?
Which 2 milliliters?
Blue until shaken, then you dark blue.
Interesting stuff.
Think about this nigga.
Yeah.
You can do it, Ella. It's not gonna explode or anything.
It's solidified as soon as it hit the bottom.
Yeah, wait, can't bother.
Are you supposed to stir it?
Pick it up so you can see better off that blue surface. There you go. There you go.
I appreciate that.
You have precipitate.
Yeah.
Cool.
Yeah, but it's
Whoa. Did it turn this into a solid?
Look at that. You do. You have a precipitate, don't you? Check that out. Don't put that on your face.
Solid now?
Yeah.
That's pretty daggone